So chapter 9 is about regulation. You can read the objectives and importance of it, of this particular chapter. So we know that enzymes act on substrate. If there is no substrate, then the enzyme cannot do anything. Yeah. So to regulate its activity, we can regulate the amount of substrate that goes to the enzyme. If you want more reactions, then the metabolite flow, we increase it a little by little, until you get the maximum velocity. So this can be done either active or passive way of controlling it through metabolite flow. Okay. Never mind that. There. This does not look like the cell, but you just have to imagine that this is the cell. And of course, the cell does not have an opening like that, opening like this. But it's just to show that nutrients get into the cell, and there are small molecules through enzymatic, through enzymatic activity, they can become larger molecules. Like for example, when you are going to form cholesterol, the precursor molecule of cholesterol is acetyl-CoA. So this is very small compound, acetyl-CoA, compared to cholesterol. Now, these acetyl-CoAs are put together by several enzymes, several steps, until you come up with your mature cholesterol. So from small molecules, it becomes larger molecules. Then that larger molecules can be degraded into small molecules so that it can be exited out if it is not needed anymore. But if some of those enzymes, of those molecules can be recycled, For example, if this large molecule is a protein, and this protein is already worn out and it has to be degraded, degradation of proteins gives you amino acids. Amino acids that are still good are recycled to become back into a protein molecule. While those amino acids that have been buttered, then they come out as waste. Now become smaller molecules and then they are removed. Okay. Now here with small molecules, still becomes small molecules, becomes large molecules. No? And this P here is phosphate, phosphorylated. Like for example, glucose. Glucose cannot be utilized unless it is phosphorylated. So the first reaction there is to phosphorylate the glucose. So this is important, phosphorylation. That is for the degradation of glucose. It needs to be phosphorylated first. Now, in relation to enzymes, these reactions, these reactions are phosphate. Enzymes, there are enzymes that when you put a phosphate, it becomes active. There are also enzymes that when you put a phosphate, it becomes inactive. So phosphorylation and dephosphorylation are two processes by which a compound can be active or inactive. Okay, so if you are going to control the metabolite flow, the flow of nutrients inside the cell, then you can control enzymatic reaction. If you have less substrate, then less products are formed. Okay, this is just an analogy, no? And this one is, as you can see, the water from this higher elevation goes to a lower elevation like this, unimpeded because there's nothing there. Well, this one, there's an impediment. You can liken this to a blood vessel with atherosclerotic plaque. So that at this area here, the pressure is high because this is very narrow already. Same as with atherosclerotic plaque of the blood vessels, you come up with hypertension. Compartmentation. All right. Another way to control your enzyme activity is through compartmentation. Meaning to say, enzymatic reactions that are opposing are not found in one area of the cell. Okay? So that means you have two types of pathways. Anabolic pathway, that is putting together small molecules to become a bigger molecule. That's anabolic. That is for growth. And catabolic is degradation. Big molecules become smaller molecules. So these two processes are not placed in one area of the cell. Some are found inside the mitochondrion, some are found in the cytoplasm. No? So it says here, anabolic and catabolic pathways that synthesize and break down common biomolecules often are physically separated from one another. Separated from one another. So that we will not come up with a useless cycle. Because if you put them in one place, anabolism going on, building a bigger molecule out of a small molecule, and if there is catabolism, that big molecule is now degraded back to small molecule. No? So it's a useless cycle. Okay? So they are found usually separated. And that is what is meant by compartmentation. And rate-limiting enzymes as preferred targets of regulatory control. Rate-limiting enzymes are usually located, but not all, are usually located at the first step of a metabolic pathway. Okay? All right, let's look at this. Another regulation is to regulate the amount of enzyme. So if there are less enzyme, naturally less reactions. No? More enzymes, then you have more reactions. Now you cannot just inject enzymes there from the outside. So you have to stimulate. If you are going to regulate, you have to stimulate the degradation of the enzyme. And if you want the increase in enzyme reaction, enzyme number of enzyme or amount of enzyme, is you have to stimulate the synthesis of the enzyme. So synthesis and degradation. No? Okay. Oh, here we are. Proteins are continuously synthesized and degraded. Enzymes here are formed from amino acid. Most of the enzymes, okay, most of the enzymes are coming from amino acid to become a protein molecule. And then this is degraded and become amino acids again. And amino acids are utilized again to become enzymes. No? But as we said, this does not occur in one place. So enzyme synthesis is found in one place away from enzyme degradation, or protein synthesis, because most of the enzymes are protein, from protein degradation. So how do we control enzyme synthesis? So synthesis of enzymes depends on the amount of amino acids present. And we know that we have essential and non-essential amino acids. Now, if your diet does not contain the essential, and then your enzyme, structure of your enzyme requires essential amino acids, then that particular amino acid cannot be formed or cannot be synthesized. So control of enzyme synthesis would mean that we start from your diet. Your diet must be, of course, balanced. That's the usual. From kindergarten, you have been told to eat a balanced diet. But they never tell you what is a balanced diet. Diba? It is up to your mother. Okay, so control of enzyme synthesis, again, is raw material. If you control the raw material for making the synthesis, you can control the enzyme, the synthesis of the enzymes. And of course, the integrity of the capacity of the cell to do protein synthesis. And you know, protein synthesis requires first the formation of messenger RNA, which is taken from the DNA, and the messenger RNA is being translated by the ribosome, no, in order that you have a protein molecule. So that is it. So if in some areas in the synthesis of protein, starting from procuring the messenger RNA from the DNA, there is a fault there, or you can control that, then you can control the enzyme synthesis. Okay. And what about control of enzyme degradation? All right. You can do that by, if you do not want the enzyme to be degraded right away, so you tend to control the degradation of enzymes. Enzymes are degraded by enzymes themselves. And if you have a control on that particular enzyme that degrade proteins, then enzyme degradation can be controlled. So it's a matter of synthesis, degradation, synthesis, and degradation. Now, in a metabolic pathway, multiple options are available for regulating catalytic site. You have allosteric regulation, and you have covalent modification. Now, we have here a metabolic pathway starting from substrate 1 acted by the enzyme represented by this arrow here, and that substrate 1 becomes substrate 2, and substrate 2 acted by the enzyme here becomes substrate 3, and substrate 3 acted by this enzyme, this arrow, becomes final product A, and that substrate 3 can also become substrate 4 through this particular enzyme, in which case the substrate 4 can become final product B by the action of these two steps here. Two steps meaning two enzymes involved. No? Or the same H4 or substrate 4 acted by this particular enzyme here becomes product C. Or this substrate 3, no? The substrate 3 here acted by this enzyme. Looks so messy. Yeah? And two steps becomes substrate D. You see? Now, we have what we call product inhibition. What does that mean? It means product feedback inhibition. Feedback. Supposing the enzyme here acting on a substrate 3 is very, very active, and this becomes high in concentration. Kasi masipag ito eh. Ito. No? And in order that there will be no accumulation of product A itself, now once in high concentration, will inhibit the function of this enzyme here. That's the arrow going that way. Okay? So that there will be no increase of what is needed. An increase of what is needed. So that the S3 here, or substrate 3, no, since this is already blocked by this one, then it can either become S4 or S5. Okay? Now, the same is true with this one. When you have already an increase or an oversupply of product B is the result of the conversion of H4 by two steps to become product B. So the same thing as product A, this is going to inhibit, again, what we call feedback, product feedback inhibition over here on this particular enzyme. You have two enzymes here. Why not here? Why did it choose to be inhibiting this one? Huh? Yes? What? Now look, you look at this. If B inhibits this, and this enzyme here acting on substrate 4 will produce a product that is inhibited here. And that product is not the final product. It's a useless product. Did you get it? That's a useless product here. Diba? All right. Like listen, for example, S3 acted by this becomes S5. Ang S5 acted by two enzymes becomes D. Now, if this accumulates, it does not stop this, it does not stop that. No? Because if you stop that, what is S5? No? This is a result of S3. So what is the use of this? This is the final product. And this is useless. So, D acts on the enzyme there. Okay? Now, what if A, B, C, D increases in amount? Where is the inhibition? All right. Oh. You can see this now. A, B, C, D. Concerted effort. No? Cooperative effort to control this one. See? Look at that. A acting on that. B still acting on this. Then we have C acting on that. And D acting on that also. Concerted, cooperative inhibition. Because all of them have increased. A, B, C, D. And that's what I mentioned earlier. Most allosteric enzymes are found early in the pathway. And this is the earliest enzyme here. While for this pathway here, that's the early, because there's only one. But this one, there are two. This is the earliest for producing B. And D here, the earliest would be this one. Do you get the idea? So multiple feedback inhibition in a branch biosynthetic pathway. And this usually happens in your body. So these are what we call feedback loops. Feedback inhibition. Oh, here is which usually has this. That's the aspartate transcarbamylase. It's a model allosteric enzyme. Aspartate transcarbamylase is the catalyst for the first reaction, which is unique, only found in pyrimidine biosynthesis. Chapter 33 here, figure 9. You can look at that up. So it is a target of feedback regulation by 2-nucleotide triphosphate. CTP, cytidine triphosphate, and adenosine triphosphate, ATP. All right. Allosteric and catalytic sites are spatially distinct. Allosteric sites are usually sites for inhibition. Allosteric meaning another area or another place of the enzyme. So where is, oh, here we are. Allosteric occupy another space, not very near the catalytic site. It should be far. Okay. So allosteric, where you have the regulation site and the catalytic site where catalysis occurs, are separated, are spatially distinct from each other. Allosteric effects may be on Km or on Vmax. You remember again our Km on Vmax? No? Remember the competitive inhibitor and the non-competitive inhibitor? Which affects Vmax? Competitive or non-competitive? Non-competitive. Okay. All right. Now, what about hormones? We'll go into these hormones when we go into the endocrine, no? Second messengers. So meaning to say that inhibition here is not direct, but through a second messenger. Second messenger. Like for example, we have not taken this up, but I will just have to talk about it. You know what is you know what is glycogen?
Yes.
Okay. Glycogen is made up of glucose. Now, when you are eating well, two organs in your body, well, there are other organs, but two, which is very, very, have a greedy appetite for glycogen, are your liver and muscle. Okay. Glycogen is made up of glucose. That is the storage of glucose when there is plenty of glucose. So when there's plenty of glucose, your muscles are going to store it. No? Meaning to say that the glucose molecule are put together to become a bigger molecule of glycogen. This is done in the liver and in the muscle, primarily, because there are other, but the amount is very, very small. But these two are very, very important as storage of glycogen. Now, when the glucose is low, glycogen is being broken down. So from synthesis, now there is a need of glucose and the person is not eating. Probably naabtan sa quarantine, no? Na lockdown, wala pagkaon. Okay. So it starts to break its glycogen, the liver and the muscle. The liver breaks down the glycogen and supplies the blood with glucose. Okay. And that glucose in the blood is now distributed to all other cells that require glucose. But the glycogen from the muscle is only for muscle use. It breaks down the glycogen, but it does not go into the blood. It is only for its own use. No? So you see two organs here. One is very generous with its natural resources. The other one is very greedy, but they have reasons for that. Okay, so in the buildup of glycogen, we have an enzyme known as glycogen synthetase. Huh? Glycogen synthetase, which puts together glucose molecules to become glycogen. On the degradation of glycogen, we have an enzyme known as your glycogen phosphorylase. Phosphorylase breaks down glycogen one glucose unit at a time. Okay, so you have two. All right. Now, the problem is that you have two opposing metabolic pathways. One is synthetic and the other one is degradation. Okay? And they are found in the same tissue. So how can you control this? Because that becomes a useless cycle. Synthesis, then degradation, then synthesis, degradation. No? Useless cycle. However, your creator put something, and this responds to the condition of the body. When the body needs glucose or the body does not need glucose. So if it does not need glucose, that means there's plenty of glucose. But when the body needs glucose, then there is low glucose in the blood. Okay, so let's go to low glucose in the blood, hypoglycemia. This hypoglycemia will now trigger reactions, creating second messengers. No? Second messengers. That second messenger, ATP, becomes cyclic AMP. And it activates protein kinase. And what is a protein kinase? Another enzyme. As kinases do, when you say a kinase, it means addition of a phosphate, a kinase. So this kinase adds a phosphate to phosphorylase and to the glycogen synthetase at the same time. No? The two enzymes that are opposing in action are phosphorylated right away. Silang dalawa. And what happens after this? The glycogen synthase or synthetase with a phosphate becomes inactive. So there is no formation of glycogen. However, the phosphorylase with the phosphate has a different action. The phosphorylase with the phosphate becomes activated. So it becomes activated, it breaks down the glycogen. Because what is needed is glucose. So the glycogen reserve is broken down by your phosphorylase that has been activated by binding a phosphate to it and becomes now active and breaks down the glycogen. So that's the story. So what brings about this? Hunger. And hunger produces glucagon, a hormone, no, which activates the formation of cyclic AMP, and that's the second messenger, because it is not the glucagon that directly stimulates the phosphorylase. So it acts by forming a second messenger, cyclic AMP. Cyclic AMP activates protein kinase adds a phosphate, the phosphorylase becomes active. Active phosphorylase acts on glycogen, breaks it down to glucose. So you see, that is the use of a second messenger. So now what about regulatory covalent modifications can be reversible or irreversible? We mentioned it already. I mentioned it already. When a phosphate is added to synthetase or to phosphorylase, it forms covalent modification. A phosphate is added with a covalent bond. And this is reversible. Reversible in the sense that a phosphatase, another enzyme, can break the covalent bond. No? Or there are sometimes, not the phosphorylase or the synthetase, when a phosphate is added or something is added to the enzyme, it becomes irreversible. Okay? So that's reversible or irreversible. Now, proteases may be secreted as a catalytically inactive proenzymes. Proteases. Now, what are proteases? Enzymes acting on protein. A very good example of this is enzymes coming from the pancreas. Now, this enzyme from the pancreas has proteases, which digest protein. Okay. Now, these enzymes are secreted from the pancreas in its inactive form. And it is only activated once it gets inside the lumen of the small intestine. They are activated there because they are powerful enzymes. Now, because these enzymes from the pancreas acts on protein and it digests. So if it is activated already from the pancreas, it is going to eat up the pancreas. And this is what happens in what you call bangungot. You know what's bangungot? Have you seen a cadaver in a bangungot? If you do an autopsy, almost all the content of the abdominal cavity is digested. That's because there is a premature activation of the pancreatic enzymes. It is activated before it enters the small intestine. And it eats up the whole pancreas. And as it comes out of the pancreas, it eats up the outer wall of the small intestine and everything that is protein in nature. That's your bangungot. Imagine enzymes eating up the contents of your abdominal cavity. But the very puzzling thing here is that the patient cannot wake up. I don't know why. Why? Because that would be a very, very painful experience. But they never wake up. You cannot hear them anything complaining. You see? So that's a problem of premature activation of inactive enzymes, where they should not be activated, no, before it reaches an area where when they are active, they cannot do damage to the surrounding tissues. So proteases are secreted as inactive proenzymes. And because of that, proenzyme facilitates rapid mobilization of an activity and response to a physiologic response or demand. Like chymotrypsin, which comes from the pancreas, it is secreted as prochymotrypsin, which requires selective proteolysis. Proteolysis meaning area of the protein molecule that is to be cut or cleave, proteolysis. As you can see this here. On top here, you have what we call prochymotrypsin. That's the inactive form. The start of activation, no? First, there is a break between amino acid 15 and 16. And so you have it here. Nah. And you have here gamma chymotrypsin. And then there's a break between 13 and 14. There is a break here in 146 and before 149. Okay. So you have a small portion, this one, made up of amino acid 147 and 148. And then you cut this off, so that becomes amino acid 14 and 15 here, amino acid 14 and 15. Okay? All right. So this now have three. 1, 2, 3 big pieces. The two small pieces are this one. The two small pieces are this one and this one. So you have 3 pieces here. Okay? And they are not separated from each other because disulfide bonds are formed. So you have here a cysteine and another cysteine in this area and forms a disulfide bond. And also another disulfide bond in here. No? Before 146, you have a cysteine residue and another cysteine residue here. So this is the active chymotrypsin. That's the active chymotrypsin. So several cleavage are performed before it is activated. So this is the active form now. So how many cleavage? How many cleavage do we have? 1, 2, 3. No? It is how it is. So activation occurs inside the intestine, but not in the pancreas, because the pancreas have no protection. Okay, have no protection from the activity of an active protease chymotrypsin. But the small intestine has a protection for that. That's why it does not eat up the intestine, the intestinal, the inner okay. This is the one I mentioned. Reversible covalent modification regulates K mammalian proteins. That's the one here. Now, a kinase adds a phosphate to this enzyme. This is a serial protease because serine is the active amino acid in the catalytic site. So this is phosphorylated. The source of the phosphate is ATP and becomes now your serial with a phosphate. Okay, through a kinase. And this is reversed by this enzyme phosphatase, which cuts this off. Okay, the phosphatase removes that phosphate and converts that into inorganic phosphate. And so we revert back to this enzyme here. Now, we do not know whether this particular enzyme, when a phosphate is added, becomes active or inactive. So it's either becomes active or inactive. Let us say that it becomes active with a phosphate. It is reverted to inactivity by removing the phosphate. So we have an inactive. Now supposing this is already active, adding a phosphate becomes inactive. Removing that phosphate there, a phosphatase, then it activates it. The one that I mentioned, glycogen synthetase and glycogen phosphorylase. Then you have acetylation, covalent addition of an acetyl group, or removal, deacetylation. It is associated with histones and other nuclear proteins. Acetylation or deacetylation. So this is involved as in glycolysis, metabolic pathways, no? Glycolysis, glycogen synthesis, gluconeogenesis, tricarboxylic acid cycle, beta oxidation of fatty acids, and the urea cycle. You can see plenty of acetylation. Acetyl coenzyme A is added. Okay. Lysine acyl transferase, acetyl transferase. Histones are proteins that are more of the basic amino acids. You know what are your basic amino acids? You have lysine, arginine. Those are basic. Covalent modification regulate metabolic flow. I give you already an example of glycogen synthesis and glycogen degradation, covalent modification using phosphate, and that phosphate, the origin of phosphate is from ATP. So a protein kinase uses phosphate from the ATP. Okay. Oh, we mentioned this already. Protein phosphorylation is extremely versatile. All right. And this shows you here. Look at this. You have enzyme and activity state. Low activity, high activity. So look at this. Acetyl-CoA carboxylase. The enzyme with a phosphate. So acetyl-CoA with a phosphate has low activity. Removing the phosphate becomes high activity. Look at this. Glycogen phosphorylase. Without the phosphate, low activity. Addition of a phosphate, increase activity. You see? Now, if you compare that with glycogen synthase with a phosphate, low activity. Without a phosphate, high activity. So they are opposite, glycogen synthase and glycogen phosphorylase. So phosphorylation, it all depends on that particular enzyme. It's either you may increase the activity or you diminish the activity or you inhibit the activity. Okay. And remind us, regulatory events. You are familiar with this cell cycle, no? Cell cycle, you are familiar with that. Okay. I think we have covered 8 and 9. And I want you to read next topic. The next topic is membranes. Let's look at membranes. Huh? So that's your assignment. Just read it ba? Just like you're reading comics lang. Sige, just read it. Just to familiarize. Okay? Do you have questions? When you don't ask question, it means that it's either you understood everything or you just don't know anything. Which is which?
Ang ikaduha daw. Jote lang.
Bagawaray may naintindihan.
Information overload.
Slight doc.
Overload.
Manwari man ito sumulod.
Tug ka na og tinuod katong ikaduha gyud dok.
Oh. Nagan kayo.
Well, this is just repeated several times. It will always be repeated. No? When we go to metabolism, this is always repeated. So, maintindihan na ninyo. Oh, ikaw, sige, go ahead. Oh, which is that? Teka. The figure. 9-7. Oh, yeah. Magnesium. You know, magnesium is very versatile element in your body. You need it. No? Okay. You have here ATP. You have 3 phosphates. The 2 phosphates, the last 2 phosphates, give off its proton. So it becomes negatively charged. Okay? Now, if you have a negatively charged molecule, when it comes in here with a positive charge, then you know what is going to result. Diba? You will have a salt bridge or ionic interaction. So what is the role of magnesium? Magnesium stabilizes the ATP here. Stabilizes that. So that's why you need that magnesium, because magnesium is positively charged too. 2 positive charges. Okay, that's the role of magnesium. Okay.
Sir, Doc, can you call magnesium an activator?
Not really. Now, magnesium, when taken as magnesium, like a magnesium sulfate, it is a relaxant. A relaxant. So it acts on proteins and relaxes the protein. Okay. When you have cramps, it means you lack magnesium. Sometimes you have hypertension because the blood vessel becomes very, very spastic. It can be relaxed by magnesium. So your antihypertensive medication should be together with magnesium. It helps.
Okay, Doc.
Okay. All right. Can we call it a day? Huh?
Doc, happy Teacher's Day.
Oh, okay.
Teacher's Day.
Oh, thank you, thank you.
Happy Teacher's Day, Doc.
Oh, thank you, thank you.
Day,
Thank
Doc.
you.
Thank you. Teacher's Day,
Thank you,
Doc.
Thank you, thank you.
Thank you po.
Thank you, Doc.
Thank
you, Doc.
you.
Thank you, Doc.
Thank you,
Teacher's
Doc.
Day, Doc.
Thank you, Doc.
Thank you, Doc.
Welcome.
Doc,
Yeah.
Tasha ni.
Oh, siya.
Please, katong, di ba na, message na you have to, ing nang imo kuan,